In this video, we're going to learn about Einstein's famous equation E equals mc squared, and also about a new kind of energy. So Einstein said that there is energy stored inside the nucleus of every atom. This kind of energy is called binding energy, and we can use his famous equation to calculate the binding energy inside an atom. Einstein's equation implies that mass can be converted into energy and vice versa. And this concept is called mass-energy equivalence. So the variables in the equation E equals mc squared have to be in SI units. However, we are going to be getting some mass units from the periodic table and talking about some common units of nuclear energy. And therefore, this topic is going to involve some unit conversions. So let's talk through those first. So to start, let's look at mass. The SI unit of mass is the kilogram. But when you get mass off the periodic table, it's measured in a unit called atomic mass units. Atomic mass units can be abbreviated as AMU or just a U. So you can convert between atomic mass units and kilograms by using the mass menu in your calculator converter, unit converter. In terms of energy, the SI unit of energy is joules. But when you talk about nuclear energy, it's common to talk about the amount of nuclear energy in terms of a unit called a mega electron volt. So the real unit of energy is called the electron volt. And mega electron volts is just a metric prefix, which means a million. Electron volts are really, really small, so we convert them into mega electron volts. So you can convert between joules and mega electron volts by using your energy menu of your calculator converter. You can go from joules to electron volts, but then you're going to have to manually convert from electron volts into mega electron volts. And to do that, 1 times 10 to the 6th electron volts is 1 mega electron volts. So that's a million. So a million tiny electron volts is 1 mega electron volt. So if your calculator tells you that you have this many electron volts, you can just divide by 1 times 10 to the 6th, or divide by a million, or just move your decimal point to the left 6 places, and then you'll know how many mega electron volts you have. You'll see this in action coming up real soon. All right, next, let's look at the mass of the particles that are in the nucleus. Let's look at the mass of the proton and the neutron. We'll look at them first in kilograms. So we notice that the neutron is slightly more massive than the proton. But it is going to be more convenient to talk about mass in atomic mass units for 2 reasons. Number 1, there are more decimal places here so that we can get a more precise answer. And we are going to want to be able to compare these masses to the mass of a nucleus from the periodic table or from a reference chart that is in atomic mass units. So we're going to start by looking at the mass of these particles in atomic mass units. All right, so let's talk about the formation of a nucleus. What if we wanted to make a phosphorus 31 nucleus? So phosphorus is number 15, so that looks like that. And so in order for us to make a nucleus, I would have to go get 15 protons. So there's my 15 protons. And we know that the mass, the atomic mass unit of every proton is this number. So I wrote that down. And then I'm also going to need 16 neutrons. And the mass of every neutron is this number in atomic mass units. And so if I add them together, this would be the expected mass of the nucleus in atomic mass units. So let's pause here for a minute. I want to point out that we do not want to round this answer off. The reason we're using atomic mass units is because we want all of these decimal places. So keep them all. All right, so this is what we would expect the mass of the nucleus to be. And so now we're going to squish all the particles together to make the nucleus. And now I'm going to go look up the mass of the nucleus. And I'm going to have to look up the mass of the nucleus in a reference table. And so this is a reference table that I took from the back of a textbook. And so that you can see here, the first column is the atomic number. Okay, so we're talking about phosphorus, which is number 15. So we have phosphorus. And we look over here, we can see there's two isotopes. There's phosphorus 31 and there's phosphorus 32. We're talking about phosphorus 31. And this column here, I'm going to go up to the top, is the atomic mass of the nucleus in atomic mass units. So this is the number that I want right there. So I'm going to copy that number down right here. That is the mass of the combined nucleus. All right, I want to point out these numbers don't match. This is what the expected mass would be, and that this is what the actual mass would be. And you're going to find that that happens all the time. The mass of the uncombined particles is always going to be greater than the mass of the combined nucleus. So there's always going to be some missing mass. The missing mass is called the mass defect. So we want to know what the mass defect is. So I'm just going to subtract these numbers, and the mass defect is 0.28 blah blah atomic mass units. And again, I'm going to keep all of these decimal places. I'm eventually going to want to take this mass defect and put it in the equation E equals mc squared. M in that equation does not stand for mass. It stands for mass defect. So it's going to have to be in kilograms. So I can go into my mass menu of my calculator converter and put in that many AMUs and convert that into kilograms. So now I know the mass defect in kilograms. It is okay to round off the mass defect in kilograms because you can see it's a really, really small number, but I have scooped up all of those decimal places and at least got them in my 4.69. All right, so the question is, where did this missing mass go? So according to Einstein's theory, the missing mass turned into energy and is now stored inside the nucleus. And this stored energy is the binding energy. And even more importantly, if I split the nucleus of the atom, this binding energy can be released. So there's energy stored inside the nucleus of every atom. And if we're looking for another energy source, we can split these atoms and get the binding energy out. Let's finish off this example. So we now know what the mass defect is. So I put that here. We're going to multiply by the speed of light squared, and the speed of light is 3 times 10 to the 8th meters per second squared. So the binding energy is 4.22 times 10 to the negative 11 joules. So you can see the amount of energy in one nucleus of phosphorus 31 is not a lot, negative 11 joules. But it's more common to talk about binding energy in the units mega electron volts. So let's convert these joules into mega electron volts. So I'm going to go into my calculator unit converter. I'll go to the energy menu and I'll put in the joules and I'll convert to electron volts. Then I'll divide by 1 times 10 to the 6th or a million, or move my decimal point over 6 places. And we find out that we get 263.28 mega electron volts of energy from splitting this phosphorus atom. All right, let's do another example a little bit cleaner and faster and see if we can get this process down. All right, so the question is, we have radioactive uranium-235, and I want to know how much energy I can get out of splitting one atom of uranium-235. So how am I going to figure that out? Well, I'm going to start by finding the expected mass of the uncombined particles. So we have 92 protons. We'll subtract and find out that we have 143 neutrons. So I would expect the mass of the nucleus to be this. But then we form the nucleus, and now I'm going to go look up the mass of the nucleus. I won't do that with you here. I'll just put in the number. And as expected, the mass of the particles is always greater than the mass of the nucleus. There is some missing mass. The missing mass is called the mass defect. I'm going to want to put this mass defect into E equals mc squared to get the binding energy. But this mass defect has to be in kilograms. So I'm going to take these AMUs and I'm going to use my mass unit converter to convert that into kilograms. Now that I have that, I can plug that in this equation. So I know my mass defect times the speed of light squared. I now know my binding energy in joules. But before I talk about it, let's convert that binding energy in joules into EVs. Divide by 10 to the 1 times 10 to the 6. And now we have mega EVs. So if I split this one atom of uranium-235, I'm going to get 1786.3 mega electron volts of energy released. Much more than that of the phosphorus isotope. All right, but remember, this is only the amount of energy in one atom. Oftentimes, when we want to create nuclear energy, we want to split more than one atom at a time. So let's look briefly at nuclear fission. So a nuclear fission reaction is the division of a heavier atom into two lighter atoms. And so here's my uranium-235. So uranium-235. And you can see it's going to break down into two lighter atoms, barium-141 and krypton-92. So how do we do this in real life? So we start the reaction by taking a neutron and bombarding the uranium-235 with the neutron. So we strike the isotope with the neutron, and that is going to create my two smaller fragments, which I don't really care so much about, but they are going to release energy and 3 more neutrons. These 3 more neutrons are significant because they then can bombard a new isotope of uranium-235 and make the same thing happen again, create 2 more fragments, some more binding energy, and they release 3 more neutrons, and now we have just started a chain reaction. So you have the binding energy of one atom, the binding energy of 3 more, and those 3 hit 3 more, and so it keeps on growing very, very, very quickly. And so nuclear fission reactions are used in a controlled sense in nuclear power plants to produce electricity. Nuclear fusion is the opposite of nuclear fission. In a fusion reaction, we have 2 light atoms are going to combine to form a larger atom. So here we have a type of hydrogen called deuterium and a type of hydrogen called tritium are going to combine to form helium. And so you can see that we have 2 smaller atoms, a 2 and a 3, are forming a 4. And if I found the mass of this nucleus plus the mass of this nucleus, it would be more than the mass of this nucleus, which means just like a fission reaction, there's going to be some missing mass. And if there's missing mass, we can still use Einstein's equation E equals mc squared to calculate the amount of energy that is going to be released in such a reaction. So fusion reactions produce more energy than fission reactions. And nuclear fusion occurs naturally in stars, and this is where stars get their energy, is such as it's bleh, bleh. Nuclear fusion occurs naturally in stars, and that's where stars get their energy. Once you run out of deuterium and tritium and you don't have the ability to form the helium, you don't have the ability for energy to be released, that's when a star would die out. All right, the last couple of things here are the reference tables. So if you need to look up the mass of a nuclei, we have page 1, which obviously goes from hydrogen down to phosphorus. Page 2 takes us down to antimony. Page 3 goes down to astatine. And then the final rows of the periodic table you can see here on page 4. So if you need to find the mass of a nucleus, you can look it up in these charts.